Hi, everyone. Thank you for tuning in to Riot's Lunch and Learn series, the place where we spotlight all of Riot's partners. Today, we have a very special partner of ours. We have Scott Vance, Senior Staff Engineer from the Wireless Research Center. For those who may not know, the Wireless Research Center is actually Riot's parent company. So I'm super excited to have Scott here with us today. Scott will be talking about 20 ways to kill an antenna. Just a couple of quick reminders before we get started. Please do keep yourself muted throughout the presentation. If you do have any questions, feel free to put those in the chat box, or you can wait till the end and feel free to unmute yourself and ask questions then. This presentation is being recorded and will be posted to Riot's YouTube channel and the meetup page where you registered for this event. And Scott has also agreed to share his presentation, so each of you will be able to find that on the meetup page where you registered as well. But without further ado, I'll hand it over to Scott. Thank you for being with us today.
Thank you, Carolyn, and thank you everyone for attending. I'm excited to talk to you today about ways to kill an antenna and in the process, ways to help an antenna to survive. As many of you know, I work at the Wireless Research Center. We do all sorts of RF and antenna design, but concentrating mainly on antennas. And so without further ado, let's talk about antennas. First of all, for the purposes of our presentation, we're going to have a few helpers today. Going to try to keep it a little bit light. So our first antenna's name is Nora. Our second one is Fred. We have a radio by the name of Bob, and we have our ground or ground plane by the name of Grant. Turns out I actually know Nora and Fred quite well. They got married just a little while back. The wedding really wasn't much to speak of, but the reception was great. And that's the thing about antennas. If everything goes well, our reception will be great. So, jumping in. What is an antenna? On a very basic level, an antenna is anything. It's a rod, it's a wire, it's another device, generally metal, used to transmit or receive radio or television signals. Antenna converts alternating voltage into an electromagnetic wave or vice versa. So antennas can send out signals, they can receive signals. Efficiency refers to how well an antenna performs its function. A highly efficient antenna, all the energy in is translated into energy out in terms of radiation. And that would be an 100% efficient antenna. In real life, you don't get 100% efficiency. You get something less, and how much less is a function of how you design the antenna, obviously. Antennas have a symbol that we use, and that symbol is down here in the lower right-hand corner. And that looks an awful lot like Fred and Nora, as you might notice. So without further ado, let's talk a little bit about the spectrum. So in terms of the presentation, I may give you just a little bit of background information, and then we're going to go into the 20 or so ways to kill an antenna. So just by way of background information, the RF spectrum consists of just a small part of the overall radio or electromagnetic spectrum. Electromagnetic energy, as you know, is everywhere. We have everything from gamma rays to long wave and everything in between. But the thing that we're concerned about really is the microwave spectrum. That's where most of our devices play. And in particular, a lot of devices tend to be between about 100 megahertz and 100 gigahertz. It's a very small part of the spectrum. Here highlighted in red, you'll see where most of the cellular phones, cellular antennas, IoT devices play right now is the 2 to 4 generation devices are around mainly between 100 and 3 to 5 gigahertz. Moving forward into 5G millimeter wave, we're going to see a lot more at higher frequencies. And bandwidth, which we'll be talking a little bit about today, is just the ability of the antenna to resonate efficiently over a group of frequencies. If you have what you call a wideband antenna, it means it can do it over a lot of frequencies. If you have a narrowband antenna, it means it just works at a few frequencies. And that becomes important because the antennas need to match the radios and need to function where the radio is functioning. All right, before we get into the nitty-gritty, why do we even care about antennas? A lot of people don't care about antennas. They kind of slap it on at the end of their design cycle and say, oh yeah, we need an antenna. Okay, is there a spot for the antenna? Sure, let's slap it here. That's not a very effective way to design an antenna or a system. But the reason why we care about antennas is because bad antennas means poor communication. The whole purpose of the antenna is to communicate. If you have an antenna, you can communicate faster. You have higher throughput. You can have a more reliable connection, and you have lower power, which means, in essence, on a battery-powered device, you have a longer battery life. Oftentimes, people fail to realize that when they make a bad antenna, they limit their battery life, sometimes by a factor of 2 or more. So good antennas, good communication, and that's good system performance and a satisfied customer. All right. The first consideration is antenna radio compatibility. You need an antenna which matches to your radio. It needs to have the same frequency. It needs to have similar impedance characteristics. You need often to provide discrete matching between the two, because if the radio and the antenna don't get along, then you don't have a good antenna system. Sometimes you need to make compromises on both sides in order to make things work. The radio may require so a certain match that it doesn't really want to see for the highest efficiency into a certain load, but when connected to the antenna, it's a better efficiency. So it's not just matching the antenna to the radio, sometimes it's also matching the radio to the antenna, but they both have to get along, otherwise you don't have a system. One thing that we often have problems with, or we see problems with in the real life, is antenna selection. Antennas are often selected at the beginning of the project, and the antenna that you choose will affect you throughout the project. And if you make the wrong decision up front, that can have a devastating impact later on in the project. The way that a lot of people select antennas is by going to a spec sheet, and there's nothing wrong with going to a spec sheet, but you have to read the spec sheet correctly. The spec sheet is based on the antenna in the most ideal circumstance that the manufacturer can imagine. It may tell you the performance, but that performance is based on the antenna being on a very specific size PCB with a specific length, width, height, etc., and maybe no components whatsoever. When you put it in a real product, sometimes the antenna performs poorly. And the reason it performs poorly is because you're putting it in a different environment. So you need to read the spec sheets carefully. You need to understand the antenna characteristics, and you need to understand that if you integrate it in a different way, you may be sacrificing gain, you may be sacrificing bandwidth, you may be sacrificing any number of other attributes about the antenna that you hadn't counted on. In a way, it's kind of like online dating. You may look at a person's profile, it may seem perfect, but when you see the actual product, it may not be the same. So make sure you understand your product, and making sure that you understand that your early choices have huge consequences down the line. The wrong frequency bandwidth. As I previously stated, all antennas have a bandwidth, and the bandwidth is where these antennas radiate efficiently. If you choose an antenna that has too wide of a bandwidth, well, it's going to pick up out-of-band noise, and it probably is going to have lower efficiency, because the wider the bandwidth for a given volume, generally the lower efficiency. If you choose an antenna, on the other hand, that has too narrow of a frequency bandwidth, it will detune easily. If you put something next to the antenna, if you load it with your hand or something else, it can slide out of band. In addition, you end up having production tolerance issues. If one antenna is slightly bigger or longer or wider than the next antenna, all of a sudden it's resonating in the wrong frequency band. In general, small antenna sizes lead to narrow bandwidths, and those narrow bandwidths tend to be more problematic than having an antenna that's too wide. So if you have to make a mistake, make the mistake on having an antenna bandwidth which is wider than what you need, not narrower than what you need. But key to all this is understanding your requirements. If you understand your requirements, you can design the antenna to match those requirements. Another problem with antennas or antenna systems in general, or if you will, a way to kill the antenna is to just choose the wrong antenna. Here we're going to be helped out by Nora and Fred. Nora is a well-rounded antenna. She has a radiant personality, and she just likes to radiate all over the place in every direction. Fred, on the other hand, is very focused, very channeled, and he is very direct. So if you have a situation where you want a networker, if you have an antenna where you don't know where it's going to be placed, you don't know which direction it's going to be facing, you're going to want a NORA. You're going to want something that's omnidirectional. You're going to want something where you don't care which it's facing. If, on the other hand, you want point-to-point communication, if you want two antennas to talk to each other and no one else, if they're in a fixed installation, you're going to want some Freds. It's not that Fred is better than Nora or Nora is better than Fred, it's that they're different. They have very different radiation characteristics, and if you choose the wrong one for your application, then you're going to be saying, I have an awful antenna, when in fact it's not an awful antenna, it's just the wrong antenna for your application. So it's key to understanding your application and your communication link first before you even start choosing an antenna. This is especially true for IoT devices. You need to understand if they're going to be installed or in a fixed location or not. In general, a lot of applications are going to want a more omnidirectional antenna pattern. And if you want a directive one, you will probably know that. One other thing to consider is polarization. Antennas talk to each other, and they do this via the signals, and those signals are picked up or not picked up depending on the matching of polarization. In the figures here, we have 4 antennas. We have the left-hand circularly polarized, the right-hand circularly polarized, 2 linearly polarized, both horizontal and vertical. This is kind of a simplification of polarization and how polarization looks, but in general, all antennas have some sort of polarization. And when the polarizations are matched, you get good results. And when the polarizations are not matched, you get poor results. One of the applications that many of you will be familiar with is GPS. GPS uses satellites to send timing signals down to devices. Those signals are right-hand circularly polarized, which means if you have a device that's picking up the satellite information, the satellite signal, and it's right-hand circularly polarized, it's going to pick that up very efficiently. If it's linearly polarized, it will pick up some of the signal. If it's left-hand circularly polarized, it will pick up very little of the direct signal from the satellites, and that's a bad thing. So in real life, like I say, most polarizations are mixed, but you need to understand your system and understand the polarization and consider this in the design process, because failure to do so can hurt your link. The wrong ground plane. Well, it turns out that antennas are made of 2 parts, the antenna part and the ground plane part. And if you don't consider the ground plane of the device, then you're going to end up in a world of hurt. The ground plane typically consists of the metal in the product that's attached to the antenna in one way or another. So in a typical device, you'll have an antenna, and then you'll have a PCB. The PCB is part of the ground plane. If you have a metal housing, that's part of the ground plane, most likely. Anything that's connected is going to have currents, and these ground currents are going to radiate. What this means is that when you take the ground plane and you twist it around, you're going to have cross currents. That's going to cause cancellation, and that's going to lower your efficiency and change your directivity. In certain ground plane environments, you have meandering or looping that can cause high impedance, which can shunt currents on the ground plane and lead to lower frequency bandwidth for the antenna, also lower radiation. Some ground planes are a very specific length, and if that length is just right, you will not only have a resonant antenna, you'll also have a resonant ground plane. This can improve your efficiency and increase your bandwidth. And done correctly, that can lead to a very efficient system. And then you have random ground planes that sometimes scatter or bend the radiation pattern depending on how they're constructed. Any number of situations can occur. But the important thing to keep in mind is that the ground plane is part of the antenna. And if you want to design a good antenna, you're going to design a good ground plane as well. Okay, one other way you can kill an antenna is to put it in the wrong position. Antennas like to be in a very specific situation or a very specific position on every ground plane. Usually for IoT devices, they like to hang out on the edge of the ground plane. The reason for this is because the antenna has a certain resonant length in the ground plane. If it's very long, the currents flow freely and it improves the efficiency of bandwidth, etc. The exact position for the ground plane will depend on the antenna type and the characteristics that you want to achieve. But if you place the antenna near the center of the ground plane, it's going to likely be directive. And if you're searching for an omnidirectional pattern, that will likely be a bad thing. Again, if you put it on the wrong side of the ground plane, you might end up radiating all of your energy into the ground. And that's useless because your device isn't in the ground in general. So you need to understand your link, you need to understand which direction you want to have your radiation, and then you need to place your antenna appropriately based on that information. The larger the ground plane in general, the more directive your antenna can be, especially if you place the antenna in the center of the ground plane. Enough about that. Squeezing the antennas. There is no better way to kill an antenna than to squeeze it. And you can do this in a number of ways. You can obviously squeeze the antenna element, make the antenna smaller and smaller, load it with high dielectric materials like glass or whatever. But you can also just squeeze the ground plane. If you make the ground plane too small, that will decrease the antenna efficiency as well. So two things suffer: one, the bandwidth; two, the efficiency. And this can be because the element is too short, too skinny, or that the ground is small. Antennas like to be big. Big is beautiful, big is efficient when it comes to antennas. Obviously, products and product designers don't like antennas to be big. And so there's going to be compromise in the design. But from the antenna perspective, the bigger antenna is generally the more efficient one. All right, one more way to kill an antenna is to block the radiation. There's different ways to do this. You can do this with metal boxes, also known as Faraday cages. You can put an antenna inside a metal box. I know this sounds crazy, but we have seen products that do just this, where they put an antenna on a PCB and then put a metal housing around the PCB and the antenna and expect radiation. Unless those devices are designed very carefully, you're going to end up getting very low efficiency from the antenna system. In addition to metal blocking the antenna, you can also end up with situations where you have head blockage. This is a typical simulation of a cell phone where you have significant blockage of the radiation pattern by the human head. It turns out humans or large blocks of water absorb microwave energy really well. So keep the antennas out of cages, keep them away from hands and bodies, and they'll perform much better. One other thing to consider is materials. If you end up putting the wrong materials around your antennas, this will kill the radiation as well. We all know that antennas themselves tend to be metal. Often the housings are metal. There's all sorts of plastics, and plastics generally perform reasonably well. Glass is very low loss, but very high dielectric, so load antennas. But spongy materials, rubbers, especially soft rubbers, natural materials that absorb water, such as leathers and carbon fibers, these can be very lossy, especially when they're placed over the antenna or between the antenna and the ground plane. Those are the two most sensitive areas on the device in terms of performance. So be careful with your materials. know what you're using and test those appropriately during the development process. Physical connections. Unless you have a good physical connection, you don't have an antenna. So contacts are very key to keeping everything working correctly. Some spring connectors are shown in the upper right-hand corner here. Spring connectors are often a good way to provide a robust connection. In the bottom right-hand corner here, you see some variable impedance structures. And what that means is if you have a coil that's going to act essentially like an inductor, if you then compress this coil by putting a contact on top of this, the coil shape will change. And as that coil shape changes, the inductance changes. And as the inductance changes, the antenna tuning changes. And it can be a big mess. So make sure that you design your contacts carefully. In addition to the electrical parameters, you need to make sure that the contacts are going to be robust through the life of the product, which means you need to consider mechanical things like fretting, lubrication, plating and plating issues. Is it gold plated? How thick is the gold plating? What other plating are you using? Corrosion, any number of issues involved here. The little joke in the center here is, hey, I know a guy, because let's face it, if you don't have connections, you're nowhere. So keep your contacts in mind and make sure you design these. In all the projects I've been through the course of my career, whenever we've had antenna failures, it's a 2-to-1 that it's actually the connector that's the issue. Antennas, for whatever reason, are a lot easier to design than connectors in terms of making them robust. Noise. Noise can make anyone hard of hearing, and this is not just parents who have teenagers who like to play loud rock music. In the case of RF systems, you have any number of sources of noise on the device. The power supply is often one of the key contributors. Charge pumps tend to be contributors in terms of the noise of the system, but there are other ones as well. Each noise source, if it's going to impact the RF performance, has not only the source of the noise, but also a coupling mechanism that can couple into the board through any number of ways, but it can also radiate out from the board, especially if there are flexes or wires involved, and that radiation can get into the antenna. If you have noise in the antenna, then the antenna can't hear, the radio can't hear. It's being drowned out through other signals, and so the antenna fails to perform its function because of the noise. So always consider noise in the design and make sure you address this early. Noise is one of the things that tends to be layout dependent, which means that if you have a bad board layout, you're going to have to spin the board to address noise issues in many cases. So make sure that you address that. I'm just noticing a number of comments here. So one of the questions here is, what would be the most common thing you see in early hardware products do wrong when configuring or choosing their antenna? The most common error that people do in choosing an antenna is choosing an off-the-shelf antenna without considering the integration of the said antenna. What we see is that a vendor will look at the spec sheet, say, gee, this meets our specifications, and they will put it in design without understanding how to integrate it. So they may put it on the wrong part of the PCB. They may not give it sufficient volume, or they may not realize that the spec sheet is optimistic based on a very specific ground plane size. So you read the spec sheet, you're going to say, oh, gee, look at this, it's 50% efficient. You put in your product on a larger ground plane, and all of a sudden it's 25% efficient because your ground plane is non-resonant, and you're saying, what did we do wrong? Well, what you did wrong is you didn't understand the characteristics of the antenna. You need to know a little bit more about the antenna sometimes than what is put on the spec sheets. So Another question from Frank, which is how can we find these problems like noise? So noise can be found a couple of ways. The first thing I would say is you need to do a good design review of your product before you can build your first hardware, because certain noise mechanisms are common, they're known, and if you get somebody who knows the common noise mechanisms, they can look at your design before you've even built anything and say, hey, this area of the board is going to be hot. Let's use these components to decouple the noise. Let's use these components to filter it so that we don't have noise after our first build. Once you've done a hardware build, you can measure it. You can slap an antenna on the device and you can measure the sensitivity of the device radiated, and you can get an indication there. There are also other ways to measure noise in terms of probing devices made by certain manufacturers that we can point you to. I'm seeing lots of questions, so let me see if I can address some of these, and then I'm going to jump back to the presentation so that we get through the slides. Lessons learned, rules of thumb for body-worn devices. Obviously, body can couple with or attenuate signals and alter any common themes you've seen. The best trick to avoiding body issues is antenna placement. If you are smart, you'll put the antenna in a place where it's not impacted by the body. I know it's not always possible, but that's the #1 rule. Nokia did some smart things years ago where they had a little indent on the back of their phone so that when you put your finger on the back of the phone, there was almost a hole for you to stick your finger in. That kept your finger away from the antenna that was only a centimeter above that hole. So you can also do ergonomic tricks to help the user know where to put their hand. Question from Chris, is simulation of any value when trying to uncover potential antenna design issues? The answer is a qualified yes. Good simulations can point to issues, and there is value in simulation. On the other hand, building prototypes is also a valid way to develop things. It depends on the complexity of your system. It also depends on the cleanliness of your system, if I can use that word. Certain systems have a lot of components very close to the antenna, and those don't simulate as cleanly as large antennas that you're sometimes using for more aerospace applications and things like that. When you have a clean antenna design, the simulation is incredibly valuable. When you have a messy antenna design integrated in your product, the simulations are more complex, they're more time consuming, they're more difficult to do correctly. They can have value, but there is also value in just building hardware. With that, I think I'm going to leave the chat for just a minute. I know I've missed some of the questions there, but let's continue with the presentation. And if you have questions specific to the slides, feel free to keep putting those up there. All right, power handling and ESD. It goes kind of without saying that if antennas get more power than they're designed for, they die. And sometimes it's kind of ugly. You get a double murder. You get the antenna knocked out and the radio. The most common way that this will occur is from ESD, which leads to a shocking number of failures. The ESD tends to kill the radio first. The receiver goes out, but when you look at the design, you look at how the radio got killed, chances are it came through the antenna. The good news is, with some clever design, you can save the radio from ESD failures, and that has to do with how you design the antenna. Late mechanical changes. I don't know how many projects I've been on where you do a prototype build, everything is beautiful, and you go into production and everything is not beautiful. And you talk to the mechanical engineer and you ask them what changed. Oh, we didn't change anything. Oh, wait, we did actually change something. So it's absolutely critical that the antenna is tuned with the final mechanics. By definition, you don't have the final mechanics until all the changes are made. So you often have to retest during development and continue to test as changes are being made. Potting is just one simple example of something that can change the antenna performance. It can shift the center frequency of the antenna by 20% or more. So Make sure that you understand what changes are happening, because everything in the end affects everything. How to avoid issues. The biggest way to avoid issues is to start early. You need to design the antenna early on in the project. It shouldn't be something that you add on after you've laid everything else out in the design. The antenna should be with you from day one. You need to choose wisely. If you're going to choose something off the shelf, make sure you understand the vendor you're using. Make sure you understand if that vendor has support or is going to help you with the tuning process. You need to understand that small antennas in general tend to be more problematic. So if you have space for a larger antenna, make your life easy, use the larger antenna generally. You need to understand that layout and mechanical issues are going to impact your antenna performance. Industrial design is one of the key drivers of antenna performance. If you have a small product, if you have a highly integrated product, it's going to require more attention to the antenna design. And so you're going to need to test early. You need to test often. After your first build, if you have the software to support it, you should be doing antenna testing. You should make sure that the antenna works early on, because sometimes solving problems takes a while. And if you need any help, we are more than happy to help you. We have a number of qualified engineers at Wireless Research Center. Most of our staff averages 20 years or more of experience. We literally have more than 60 patents for members of our staff. So we're well versed in antenna issues, and we're happy to provide assistance where we can. And with that, I just want to thank you for your time today. Let's go and look through questions and see what I've missed here. So I see a question from Edward. It says, how do I test the antenna? Is there software, hardware? I'm working with 4.5 gigahertz Wi-Fi. So to test a 4.5 gigahertz antenna, a Wi-Fi antenna, there's a couple of different ways to test it. There's passive testing and active testing. Passive testing refers to just testing the antenna itself without the radio. Active refers to testing the antenna and the radio in a combined system. We recommend testing both. The passive testing will tell you how good your antenna is. The active testing will tell you how good your system is. Certain things like noise, you will not see in the passive testing. You'll see those first when everything's hooked up to the radio. In terms of how do you test it, I should have probably put a picture of a test chamber in here. It's not in the presentation, but we're happy to address that with you offline. There's lots of good ways to test these. There's anechoic chamber testing. In addition, there's actual user testing or field testing. There's ways that you can set up your device in known environments, office-like environments, and we can do use testing in addition to the chamber testing. Both are useful. The field testing can be very useful on 2.4 gigahertz devices because you often have multiple antennas and MIMO impacts, and that changes depending on your channel model, which is maybe a little bit more detail than we wanted for this presentation. But there are good ways to test this. I'm going to look through and see if there's any questions that I've missed here in the chat. The most surprising cause of signal or antenna failure in all of your past projects is a question from Chris Meyer. Chris, I don't know how to answer the most surprising failure, but I will tell you one of the most painful failures that I've come across, and that is metallization. I used to work on some products which used vacuum metallization on the housings, and the vacuum metallization is a very thin coat of aluminum. It turns out that if you do it just right and just the perfect thickness, you can make it nice and shiny, which our designers love to have shiny products. And if you do it a bit wrong, then the aluminum gets too thick, it becomes a conductor, it was placed close to the antenna, which means that all of a sudden we're shorting the antenna to ground, the antenna impedance shifts, everything got really bad. So we had to come up with some production methods to make sure that we could effectively test this vacuum metallization process in high volume production. And that was a failure that we only saw when we started doing mass production, because the prototype samples were perfect. So sometimes you end up with painful things like that. Hopefully that's a useful example. I am at the end of my presentation. If there are any other questions, I'd love to take those at this time. And if not, you all just got yourself 20 minutes of free time back in your day.
Thanks so much, Scott. Yeah, as Scott said, if anyone has any questions, feel free to put those in the chat box, or you can unmute yourself. I encourage you to reach out to Scott if you have additional questions you think of later. Of course, you're always able to reach out to the Wireless Center at info@wrc/nc.org, or you can also reach out to me as well, and I'll put my email there and I can connect you. But I thank you all for being with us today. Again, you'll be able to find this recording on Riot's YouTube channel and the meetup page where you registered. But
I've got a couple questions.
Yeah, go ahead, Russ.
Yeah, apologies. I'm also working out, so this is during my lunch period. But would like to dive into more details, specifically around channelization. This was extremely basic. I'm looking more for, antenna types for different uses, LoRaWAN, IoT, Wi-Fi, 5G, low band, mid band, millimeter wave, massive MIMO support, CA, DSS, that sort of thing.
Yeah, so you mentioned about 8 or 10 different technologies there, all of which have their unique challenges, and all of which are going to depend on the exact applications that you're looking for. Do you have a specific question regarding all of those, or what would you like?
Yeah, I was just thinking it's probably good to cover some of those as basics, including the channelization, whether it's TDD or FDD, some of the FCC regs. You kind of mentioned IoT, but then you mentioned a Nokia phone, so you opened the door.
Sure. So I guess what you're asking for is a future presentation where we go into detail on some of these technologies or channelization or more details. Is that what you're asking for?
Yeah, and I think people should realize when you get to 5G antennas and radios, it's extremely complex. And you have, you've got the ORAN architecture, you've got a lot of the virtualization, you've got power requirements. And then I think the other topic on interference, a data-driven model or evidence-based model would be valuable.
Absolutely, and we do have specialists in a lot of those fields, particularly when you get to millimeter wave, the whole antenna structure changes. I didn't even cover any antenna structures here, but obviously for each of these bands, you have different physical structures associated with the antennas, in addition to the channelization, the models, and things of that nature. I tend to specialize in product design. We have other engineers who look more at the channel models. And certainly we could give something in the future which deals more with the channel models or things of that nature. And if you have any specific questions, feel free to drop us a line and we could put you in touch with the correct engineers for those.
I think it'd be a good lunch and learn to cover things like massive MIMO, especially for millimeter wave. And sure. I think the channelization you covered earlier, I think was wrong, but you get very wide channels in millimeter wave.
Sure, millimeter wave, it's all about bandwidth, and you have very wide channels associated with those bandwidth. So yeah, we'd be happy to address additional topics going forward.
The other key topic I think would be coexistence, especially in 6 gigahertz.
Coexistence, correlation matrices, all of those are excellent topics. and a little bit more advanced than we wanted to touch in this presentation, but certainly those are design issues that we deal with.
Awesome. So it sounds like we have some great suggestions for future Lunch and Learn topics. I know Shruti Sora at the Wireless Center has signed up for some, so we can definitely suggest those to her. Thanks so much, Russ. Awesome. Any other questions before we close it out? All right, everyone. Thanks again. Thank you, Scott, for being here with us and answering all those questions. I hope everyone has a great day. Take care.
Thank you.